Hi, thanks for your interest in watching our presentation. I am Ali Safa and I am a doctoral researcher at IMEC and the KU Leuven in Belgium. In this presentation, I will go over our work on FMCW radar sensing for drones using variational autoencoders. In this work, our goal is to explore the use of radars and variational autoencoders for performing useful drone tasks, such as velocity estimation and distance to obstacle estimation, using a radar mounted on a drone. Indeed, radars are gaining interest in drone applications due to their ability for robust range, angle, and velocity estimation under harsh circumstances. At the same time, deep neural networks have been gaining large interest for radar processing as well, but generally require the retraining of networks from scratch for each task at hand, given the very high dimensional nature of millimeter wave FMCW radar data. In contrast to retraining of DNNs for each new task, we explore in this work to which extent unsupervised learned lower dimensional radar representations, such as representations learned by variational autoencoders, or VAE for short, can be reused for various kinds of downstream tasks. To this end, our contributions in this work are the following. First, we release a first-of-its-kind dataset of jointly acquired raw radar ADC data and RGBD data, meaning camera and depth sensing, captured on a flying drone. Then we provide various convolutional VAE architectures acting on different radar input formats. And we conduct numerous benchmarking of our proposed approach on tasks such as drone velocity estimation and distance to obstacle estimation. Now let us cover our data recording setup. In this slide, a picture of the drone setup that we have used to acquire all our data is shown. The drone is equipped with a 79 GHz FMCW radar with 2 transmit antennas and 4 receive antennas. It also embarks a RealSense camera, providing both RGB video output and depth sensing. All data is recorded using the onboard Jetson Nano platform. Data is recorded by flying the drone under different scenarios in an indoor, warehouse-like environment composed of open spaces and storage aisles. The drone is remote controlled by a human pilot. In this work, we recorded data under 3 different flight scenarios. Scenario 1 consists of flying the drone through the storage aisles in loops. This acquisition was the longest and is used to train our various VAEs as an independent train set from the data that is collected in the scenario 2 and 3. Scenario 2 consists of flying the drone in the open area from one wall to the other, back and forth. Finally, scenario 3 consists of making the drone hover with light movements in front of a corner reflector. The dataset that we acquired in this work contains both the raw ADC data of the radar as well as RGBD data captured by the RealSense camera. It also embarks the internal inertial state of the drone controller. In addition, we also record the ground truth positioning of the drone using a motion capture systems for scenario 2 and 3. All the data is synchronized with the radar frame rate at 5 frames per second. Finally, we also include already processed range Doppler and range azimuth maps in our dataset, obtained from the raw ADC data, using Cape and beamforming in the case of the range azimuth maps. The radar and camera parameters are given in the table shown in this slide. Doing so, a total of 38 GB of data is therefore released to help future research. For illustration purposes, this slide shows a few examples of jointly acquired radar and RGBD data captured on our drone. Now let's overview the various neural network architectures that we use in this work. As explained in the introduction, the goal of this work is to explore to which extent radar representations learned by unsupervised models, such as VAEs, can generalize and be reused in a number of different downstream tasks. In this work, we will employ convolutional VAEs that we will train once on the radar data of scenario 1. Then we will reuse the already trained encoder in a variety of drone tasks, such as velocity estimation and distance to target estimation. The VAE framework is a non-supervised learning framework which allows learning of the latent statistics of a certain data source, noted Z in this slide. A VAE is composed of an encoder and a decoder network. The encoder network acts as an approximate posterior model and infers the latent state Z given the input, while the decoder acts as a likelihood model, estimating the expected observation, meaning the input that we are expecting, given the latent state. The latent state is generally assumed normal distributed, following a standard Gaussian distribution, noted N01 here. As usually done in a variational Bayesian inference, training is done by maximizing the evidence lower bound, or conversely, by minimizing the loss function L shown on this slide. Doing so, the decoder is trained to produce likely observations from states, while the encoder is trained to produce likely latent states Z that minimizes their callback labeler distance, meaning their statistical divergence, with regard to the N01 distribution. Compared to normal autoencoders, VAEs have been shown to produce better generative spaces with better separability between the components of the latent states. In this work, we consider 3 different VAEs acting on 3 different radar input types. The first architecture processes range Doppler maps and is termed RD-VAE. The second architecture we consider processes range azimuth maps obtained via cape and beamforming and is termed RA-VAE. The last architecture processes raw ADC data of only 2 consecutive chirps, and we term this model the CVAE for chirp VAE. With the chirp VAE or CVAE, we want to see how well we can perform useful drone tasks using only 2 consecutively transmitted chirps, in order, of course, to lower the power consumption at the radar site. The CVAE decoder is composed of a first decoding branch, which minimizes the mean square error with regard to the range Doppler maps, and also has a second decoding branch, which minimizes the mean square error with regard to the range azimuth maps. The detail behind the network architecture for each setting is given in the table shown in this slide. Both the RD-VAE and the RA-VAE use a 6-layer encoder with 2D convolutions, while the chirp VAE, or CVAE, uses a 5-layer encoder with 1D convolutions, since it acts on raw ADC data. All VAEs are pre-trained in a non-supervised manner using the data from scenario 1 only. Doing so, we obtain 3 VAEs which encode the high-dimensional radar data into low 64-dimensional representational vectors. Next, we will evaluate how well these learned representations can be reused to perform a series of drone tasks, such as velocity regression and distance to target estimation. Now, let's move to our experimental results. The first experiment that we conducted consists of regressing the distance of the drone to the wall towards which it is heading. This corresponds to the data acquired in scenario 2. The ground truth distance is provided by the motion capture system. We use our already trained encoders and we add to them 2 additional layers of fully connected 128 neurons at the output of these encoders. We train these additional layers in order to perform distance regression using 5/6 of the data in scenario 2 and using the ground truth distances from the motion capture system as target values. The remaining data is used for assessing the regression performance. We compare the performance of the various VAE models against the conventional radar processing baseline, which consists of detecting the highest peak in the range azimuth maps in order to obtain the distance to the wall. The table shown in this slide summarizes the results in terms of mean square error with regard to ground truth, also in terms of median error, and also in terms of interquartile range. The best performing model is the RD-VAE in this case, while the conventional radar processing baseline suffers from outlier type peaks, which can be seen on the graphs in this slide and also evidenced by the lower interquartile range. In our second experiment, we now estimate the velocity of the drone from the radar data of scenario 2. Ground truth velocity is again provided by the motion capture system, and we report the error performance of the velocity regression in the table shown below. In this case, the RD-VAE model is also the best performer as expected, since it directly acts on Doppler processed data. In our third experiment, we place a corner reflector in the middle of the environment, and we make our drone hover with light movements in all directions in front of it. So this corresponds to the data acquired in scenario 3. The goal here is to regress the distance to the corner reflector. In this case, the best performing model was the RD-VAE as well. Finally, our fourth and last experiment consisted of estimating the angle of arrival from the drone to the corner reflector. In this case as well, the motion capture system is used to acquire the ground truth data, in this case the angle. This ground truth is used to train or to fine-tune the two fully connected layers of 128 neurons that we added on top of the already trained VAE encoders. In this case, the RA-VAE, meaning the VAE acting on range azimuth maps, was the best performer. In this case as well, we remark the presence of outliers in the case of the conventional radar processing pipeline, which is also evidenced by the lower interquartile distance in the error metrics. In this table, we summarize and discuss the obtained results for each of the 4 experiments we conducted in this work. In general, we saw that the RD-VAE, meaning the VAE acting on the range Doppler maps, was the best performing model for tasks where distance and velocity had to be estimated. When it comes to the angle estimation, we saw that the RA-VAE, meaning the VAE acting on the range azimuth maps, was the best performing model. Regarding the conventional radar processing pipelines, which consisted of identifying the peaks of highest amplitude in the various radar spectra, we saw a significant presence of outliers, as evidenced by the lower interquartile distances. Finally, we also remarked on this table that even though the CVAE, meaning the VAE acting on the successively emitted 2 chirps, was not the top performer, of course, but still it coherently captured distance and velocity information with lower mean square error compared to the conventional radar pipeline in the distance regression tasks. This was again despite using only 2 consecutive chirps. Therefore, since the CVAE setup requires the radar to use only 2 consecutive chirps, it could constitute a lower power and latency alternative to the acquisition of full resolution radar maps, at the cost, of course, of less accuracy. So to conclude, we saw that in this work we first acquired a novel dataset capturing joint radar and RGBD data from a flying drone. We released the dataset for helping future research as well. Then we conducted several experiments using variational autoencoder models, and we saw that VAEs are a promising solution for learning reusable radar representations. We also demonstrated that the chirp VAE approach provided meaningful results despite using only 2 consecutive chirps. Therefore, we believe that this might be an interesting avenue for future work. Indeed, different chirp encoders using, for example, recurrent layers could be further investigated to enhance the results. Using the recurrent architecture, it should be possible to adaptively increase the number of chirps in order to improve accuracy only when needed in an adaptive way. This will provide a radar power consumption versus accuracy trade-off. Thanks a lot for your attention.